Hello wonderful person, this is Anton, and in this video we're going to be talking about a topic that I've mentioned previously in many videos, but never really thoroughly explored. We're going to talk about the Final Parsec Problem, which refers to the collision between supermassive black holes. Let's talk about this, and welcome to What the Math. When it comes to black hole collisions, we've seen quite a lot already. As a matter of fact, pretty much every single week now we detect at least one somewhere out there in the universe. But all of these black hole collisions are actually much smaller black holes. These are so-called solar mass black holes, which are normally around 10 to maybe 30 masses of the Sun, much smaller than the so-called supermassive black holes that we usually find in the middle of various galaxies. And the detectors we're currently using are actually not even capable of detecting these supermassive black hole collisions simply because of the way that they're designed. So the most famous detector, or actually the pair of detectors known as LIGO, which is in the US and is very active in detecting various black hole collisions, is essentially set up to detect frequencies between 10 and 1000 Hz. Now, what this means is that as black holes come closer and closer together, at some point the frequency is going to be around 10 Hz, the frequency of the gravitational waves that they emit, and then it will increase to about 1000 Hz. And then it will probably increase even more, but we're not going to be able to, I guess, in a sense, see it or hear it. But we are able to detect everything between 10 and 1000 Hz. However, this is for smaller black holes. Larger black holes, specifically supermassive black holes in various centers of various galaxies, are obviously moving much slower around one another, and if they do produce gravitational waves, they produce much lower frequencies. Here we speculate that the frequencies are possibly even in nanohertz. That's basically 1 divided by 1,000,000 hertz, and currently we're just not able to detect this. So even if there were two supermassive black holes orbiting around one another and potentially collide with one another somewhere out there in the universe, currently we just can't really detect it using LIGO. We can, however, detect it using another method known as the Pulsar timing arrays, and this image here will hopefully sort of help you understand this. So today we know that there are various pulsars around the galaxy, and these are extremely accurate neutron stars that produce very specific and very unique pulsations that we can detect from very far away. If, however, a large enough gravitational wave approaches, it will slightly change these pulsations, and we'll be able to detect this by looking at various pulsars out there. This image from David Champion kind of shows you what's happening here if a really large gravitational wave passes through planet Earth and through the solar system, and we'll be able to see that some of these pulsars will no longer align or will no longer produce similar pulsations, and this will of course mean that a very massive gravitational wave has just passed through us. Now this particular type of detection is still in its infancy, but the Chandra X-ray detector that you see on the screen right here is usually, theoretically at least, capable of detecting this. So far we actually haven't really seen anything that would be from a supermassive black hole. And we also think theoretically maybe it's not even possible. And for this reason I need to explain to you what we mean by the so-called Final Parsec Problem. Now, a lot of really detailed information on all of this, and of course some of the solutions to this problem, are in this amazing thesis by Fazel Khan, who's now an associate professor in one of the German universities, and he wrote this really extensive paper explaining the Final Parsec Problem and potential solutions. And you can of course find this paper in the description below. So what exactly is this problem? Well, today we know that there are quite a lot of galaxies out there that have binary black holes. Here's an example of one where you can clearly see that there are at least two sources of emission of energy, suggesting that this is a galaxy that most likely collided with another galaxy, and now there are two supermassive black holes sort of going around one another. These supermassive black hole pairs are quite familiar to us, but there's one problem. We also know that there are a lot of galaxies that have single black hole, like for example the Milky Way. And we of course think that the way that this black hole grew is by essentially colliding with some of the other black holes from other galaxies. In other words, pretty much most of the supermassive black holes in centers of various galaxies out there have a chance of having been formed through massive collisions with other black holes. But here's the thing though. if you were to look at this theoretically, and if you try to crunch the numbers and try to calculate if it's even possible, you would actually be sort of stumbled upon what's known as the Final Parsec Problem. And I think this image here explains it relatively well. So when these supermassive black holes are really far away from one another, they have a lot of stars orbiting around them, including a lot of really large globular clusters, a lot of massive stars, and a lot of just gas in general. But as this gas finds itself between those two supermassive black holes, in other words, let's take a look at this miniature model. Here are two supermassive black holes, except that they should be thousands of light years away from one another, and between them is this star. As this star passes by here, it will very likely transfer its orbital energy and will probably just either get kicked out of the galaxy or swallowed by one of the black holes. And as this happens, the black holes will actually lose a little bit of energy and move closer to one another. So let's see what happens in this simulation. We basically will affect one of the black holes in some way. And you can see that the star fell in, and right away you saw how the two black holes collided. Now this was a very miniature example, and it's something that obviously doesn't happen on these scales, but if these two black holes are really far away from one another and there's a lot of stars between them, at some point they will actually find themselves much closer, because all of this energy that was stolen from these stars that were either kicked out or swallowed will eventually be transferred away from the black holes, and they'll find themselves within about a few light years away from one another. And this is also known as the dynamical friction here. And so here, within this area, they'll be able to use the stars and the gas between them and so on and so forth to lose enough energy to move closer. But then they actually reach the point right here where they're sort of still far enough from one another to experience the gravitational wave effects, but not far enough to have anything between them or to experience more dynamical friction. In other words, at some point, these two black holes are going to be maybe about 3 to 4 light years away from one another, where there's really nothing between them anymore, so nothing to kind of steal energy from. But because they're so far away from one another, they're still not really experiencing enough gravitational wave effect, which is usually responsible for doing what you're observing here. As these black holes move closer and closer, the gravitational waves make them lose even more energy, and they move even closer. And basically this effect sort of multiplies to the point where the black holes collide. But for this to start happening, they really need to be much closer to one another, possibly within a few astronomical units, or basically several times closer than they currently are. And so this distance, that's usually 3 to 4 light years, is around 1 parsec. And it's a problem. We don't really know how two black holes that are roughly around 1 parsec away from one another can then come closer, because gravitational waves are still not really affecting them, there are no stars between them, and technically they should be kind of stuck here for billions or even trillions of years, because it would take a very long time for them to sort of attract each other and for them to come close enough to finally start experiencing gravitational waves. And this Final Parsec Problem has been, well, technically a theoretical problem for a very long time. Now, we've seen at least 2 galaxies where the black holes are actually surprisingly closer than 1 parsec. One such galaxy, known as OG-287, is roughly around 3.5 billion light years away from us, and we've detected a very unusual pattern around it. Every 12 years, it seems that something passes through its accretion disk and creates these patterns, suggesting that there's another supermassive black hole orbiting it. In other words, it sort of looks like this. There is a supermassive or ultramassive black hole with 17 billion masses of the sun in the middle, and another smaller black hole, roughly around 100 million masses of the sun, orbiting inside of the accretion disk. As you can see, the distance here is roughly around 1/5 of a light year, suggesting that somehow these black holes managed to get closer. By the way, just to give you a comparison, our black hole in the middle of our own galaxy is about 25 or so times smaller than this one, and a lot smaller than that one. But anyway, so this example here seems to suggest that somehow black holes can make it closer. And there's at least one more example. The galaxy known as PKS 1302. This particular quasar, at a very similar distance of 3.5 billion light years away from us, exhibits a pattern that repeats every 5 years or so. And here, We think that it's two supermassive black holes orbiting around one another every 5 years, creating these unusual effects. And the distance between them is probably somewhere around 2000 or so astronomical units, which is basically 2000 times the distance of Earth to the Sun. Now, this is a lot closer than the previous supermassive binary pair, and this also suggests that, well, at some point they should be actually colliding with one another. Not anytime soon, but within a few billion years from now. And the discovery of these binary black holes that are very close suggests that somehow the galaxies are able to overcome this final parsec problem. Now, we still don't really know how. We don't exactly understand what can actually cause the supermassive black holes to finally start coming closer together. But in his thesis, Dr. Khan suggests that since most galaxies are not perfect spheres, there are always going to be imperfections between them. And that includes, of course, having various amounts of stars that do end up coming toward those two black holes, even if they're only 1 parsec away from one another. The simulations he ran suggest that it might happen within a few billion years, that at some point several stars will make it in between those two black holes, and through the effects of dynamical friction, they'll basically transfer their energy to black holes, making them move closer. Now that's one suggestion. The other suggestion comes from the so-called triple black hole systems. We've actually talked about the discovery of several such systems in one of the previous videos, but here this is one of the more recent discoveries. The simulations suggest that the third supermassive black hole, even if it's not as massive as the other two, will allow them to slowly merge with time, assuming of course that the 3 galaxies that collide do so in a manner where the 3 black holes will then kind of orbit around one another. With the simulations that we have, the idea here is very simple. It's basically a 3-body simulation with 3 bodies not really having stable orbits. So at some point they'll very likely collide with one another and then combine into one large object. Now obviously this is just a speculation, but for now the triple galaxy, or having 3 galaxies collide instead of 2, is one of the solutions to the parsec problem. So in other words, maybe most galaxies that have a very massive black hole in the middle actually had triple galaxy collisions, not just double galaxies. And so both of these are, I guess, somewhat reasonable solutions to the final parsec problem, but as of today none of them is a definitive solution. So basically, as of 2019, when I'm making this video, the common understanding, scientific understanding and acceptance is that we don't really know how supermassive black holes collide. We don't really have a mechanism for them to combine into one, and if one day we're able to detect gravitational waves suggesting a supermassive black hole collision, we'll have serious trouble explaining it. But we actually hope that we do one day. This is kind of the next goal for both LIGO and other detectors. We hope to find a supermassive black hole collision and then explain it using various models that might be proposed later on. For now, it's basically a paradox and a kind of a mystery of the universe. But anyway, on that note, hopefully now you know a little bit more about the final parsec problem, and hopefully this is clear to why it's a problem. In some of the future videos we'll discuss more mysteries, but for now that's it. Come back tomorrow to learn something else, maybe consider supporting this channel on Patreon, and maybe subscribe. I'll see you tomorrow, space out, and as always, bye bye.